All right, time for our final lesson in thermochemistry, all about heat curves. So this is a pretty cool lesson. It puts together a lot of what we have already been working with. We're going to do both, calculate the energy to change the temperature of a substance, and calculate the energy to change the state of matter, which is what we started off doing, the delta H vapes, the delta H condensations, delta H solidifications. So we'll put them all together and work with what we call a heat curve. Now we will only specifically look at water, and you'll be given all the variables and the equations you need. You just have to know where to use them. And that's where a heat curve comes into play. So on one axis, you'll notice we have temperature. On the other, we have energy. And here's a line. Let's say we're driving up the temperature of water in order to find out how much energy, and there's energy down here, we symbolize it as a Q in the equation, in order to figure out how much energy it's going to require to heat that water, again, from a given temperature, here'd be the temperature, to a different temperature up here. We'd use this formula here. How much water do you have? The mass times the specific heat, which is 4.184, and then times what that temperature change is from here to up here. But the idea is you can only raise or drop the temperature of water so far. And then you have a phase change. Hopefully you guys are familiar with the range at which liquid water exists. So 0 degrees to 100 degrees Celsius. Make sure you guys are very familiar with this as we move forward. So if we're going to start off going backwards at first here, we have melting. When we get to 0 degrees, melting. Again, that happens at 0 degrees. You are responsible for knowing that 0 degrees Celsius there. And again, to figure out how much energy it takes to melt the ice and turn it into water, we use the formula mass times delta H fuse. And then we have two values, so watch what you're looking at or what you're using, 334 joules per gram or 6.01 kilojoules per mole. Once you get your ice, and notice we don't have a temperature change, there is no temperature change while we're going through a phase change. It's not in the equation either. Here's delta T on this equation, but it's not in the dark blue equation. As we go from water to ice, or vice versa, from solid ice to liquid water, we will start at 0, we'll end at 0. There is no phase change. In this case, we have reached the point where all of our ice is now, or all of our water is now ice, and we can continue to drop the temperature of that water. Again, the formula there is the exact same as the formula up here. We're trying to find how much energy to lower the temperature. Q is equal to the mass, however much ice you have, times the specific heat, times the change in temperature. Again, notice you have a different specific heat. It's now ice, it's now solid, it's not the 4.184 anymore. Now we're working with 2.1 as our CP for ice. Again, you'll be given these variables. They'll be listed for you on the test. Just make sure you know to use the right one on the right part of the problem. All right, so we have our ice. We've brought the temperature up. We figured out how much energy that takes. We've melted it. We figured out how much energy that takes. We've brought the temperature up. We found out how much energy that takes. Next step would be to vaporize that water. So to go from liquid to gas. Again, this happens at 100 degrees Celsius. Don't forget that. You'll have to know that a lot. So at 100 degrees Celsius, our liquid water will vaporize to gaseous water. Once again, we have no temperature change. It's flat right here at 100 degrees Celsius until all of our water, all of our liquid water has turned into water vapor or gas. Again, that formula is the same as the formula to turn it to ice or melt the ice. We're looking for the amount of energy. We use the mass times the delta H vape. Again, this will be given to you, but make sure you remember, if you're vaporizing, you have to use the delta H vape. And then watch your units. You'll have two of them given to you. So watch your units. It's either 2260 joules per gram or 40.7 kilojoules per mole. All right, final step on our heat curve is going up right here. Once we have all of our liquid water now turned to steam, we can continue to raise the temperature of that steam. And hey, guess what? There's that exact same formula from here and from here. Anytime you're changing the temperature of something, whether it's water, which is what we're working with now, or a metal, or a rock, or anything, anytime you're changing the temperature, it's going to be this formula here, mass times specific heat times delta T, or change in temperature. And then the only real difference that we're working with between these three is that now that we have water vapor, the CP for vapor is different than it is for ice or liquid water. It's 1.9 joules per gram degree Celsius. And if you're not familiar with the 0 degrees or 100 degrees Celsius, you need to learn them. You need to know when to stop and melt the ice, or stop and freeze the water, or when to stop and vaporize the water, or when to stop and condense the gas. That'll be a big part of this chapter. Again, you'll have something on the test that looks a lot like this top portion. You'll be given all the variables that you need, all the equations that you need, all the symbols that you need. You need to make sure that you understand when to use which ones. You would not be given the graph. You'll probably be expected to draw the graph on your own. And it really does help to take the time and draw it out on every single homework problem to figure out what steps you're going through, what calculations you need to make, and how many total calculations you'll be needing to make. All right, some example problems. Problem 1, again, there's my heat curve. I drew it out myself. That's going to be a necessary component as you guys are working through your homework problems. So get used to drawing this general shape, and I'll show you in a minute here how and where I start to mark it up. So sample problem 1. How much heat, that'd be Q, is required to raise the temperature of 25 grams of ice at 0 degrees Celsius to water at 25 degrees Celsius? All right, well, I take a look at the problem that I have. I have a mass, I have a melt, that's a delta H melting there, delta mass times delta H will get us that. And then we have to raise the temperature by 25 degrees. My heat curve is going to help me figure out what steps to make. I'm going to draw a little mark right here that tells me where I'm starting. Ice at 0 degrees, so I'm on the ice side at 0 degrees. And then another mark here because I need to take my temperature up 25 degrees. My first amount of energy is going to be how much energy to melt that ice. It's my Q1. My second amount of energy is how much energy then to bring my now liquid water up to 25 degrees. It's going to take 2 steps. It's the importance of the heat curve. That's why we have it, why we use it. Our total amount of energy will be our energy from the first part plus the energy of the second part. All right, without further ado, let's get started. Our mass is 25 grams of ice, and that shouldn't change. Our delta H melting, or delta H fusion, is 334 joules per gram. Just set it up like a factor label, cancel out the grams, and we'll end up with 8,350 joules of energy will be required to melt our 25 grams of ice. You can notice the underline there. It's showing me 3 significant digits. 1, 2, 3 here, 1, 2, 3 here. So 1, 2, 3 there. My second equation, I'll have to use M times CP times delta T. My mass is 25 grams. Again, that shouldn't change. My C of water is 4.184 joules per gram degree Celsius. And my temperature change, again, always final, 25 degrees minus initial. I want to make sure I get my signs correct, positive and negative. So final, I'm going up to 25 degrees. I'm starting at 0 degrees. You can crunch those numbers, and I'll get a second amount of energy, the amount of energy required to go from water at 0 degrees to water at 25 degrees is going to take 2,615 joules. Once again, I've underlined the digit that is not significant. I've got 3 there, 4 here, 3 there. So I should have 3 in my final answer. I don't round it off because I'm not quite done. I've got one more step to do. I need to add together my Q1 and my Q2, and this is why it's important to have those numbers underlined, because now that it's an addition problem, it doesn't matter how many significant digits I have. What matters is what placeholder the last significant digit is in. In both of these numbers, the tens column, so there's the 5 there in the tens column, and the tens column, I have a 1 there in the tens column here, both of these numbers go to the tens column. So our final answer should have its last significant digit in the tens column. It doesn't matter how many total digits we have. Notice I've gained an extra digit and I have 1, 2, 3, 4. That's fine, that's okay. It was an addition problem. I've got one more digit, but my last digit is in the tens column. That's what's important. I'm going to look over here at the 5. That 5 is going to tell me to round up. So my final answer should be 10,970 joules. Kind of rounded that 6 up to a 7, and there's our answer. Let's try another one. So how much heat is required to heat or raise the temperature of 11.5 grams of H2O at negative 25 degrees Celsius to water at 15 degrees Celsius? Hey, do you remember on that last slide when I told you it's going to be very important that you know at what point water melts and at what point it boils? Well, here's that type of problem. You'd be surprised how many times people try to take water straight from negative 25 degrees to 15 degrees and forget about this step right here. Don't forget about that. So again, I've got my heat curve. It's going to help me set up my problem. I'm starting way down here. I'm below the freezing point, and my first amount of energy is only going to bring me up to 0 degrees, because my next step is going to have to melt the ice, and then finally a third calculation to bring my now 0 degree water up to 15 degrees of water. So this one's going to take 3 total calculations to figure out how much energy to raise the temperature. And the total amount of energy will be the sum of all 3. All right, so let's get started. My first Q will be found by the mass times specific heat of the ice times the change in temperature that I wish to make. So 11.5 grams. The CP of ice is 2.06, or I think I gave you 2.1 on the last page. Got 3 digits here, so this one's probably better. And then my change of temperature, watch out for this. We can only take ice up to 0 degrees. Don't try to put in 15 right there. That's not accurate. So our final temperature for the ice will be 0 degrees. We started our initial temperature at negative 25 degrees. So that means we have a 25 degree change in temperature. So my total amount of energy to heat that ice will be 592.25 joules. My second energy, so now we're right here. Now we need to melt the ice. I use my delta H fuse, 334 joules per gram, and I find a amount of energy of 3,841 joules to melt that ice. And then finally, a Q3, we're going to need to bring the temperature of that now 0 degree water, that liquid water, up the final 15 degrees. I wanted to get it up to 15 degrees Celsius. So here's my 11.5 grams. I'm assuming I haven't lost any water yet. My specific heat of liquid water, and then my temperature change. Again, do not go down to negative 25. That's not where we're starting. This step starts at 0 degrees Celsius. That's where the water became liquid, and it goes up to a final temperature of 15 degrees Celsius. So we crunch the numbers. We get a Q3 of 721.74 joules to heat the water 15 degrees Celsius. Again, I've done a good job taking care of my digits. I throw out my numbers. I know this is a plus plus an addition problem. All of my numbers have a digit in the tens column. So that 9, that 4, and that 2, they're all in the tens column. So my final answer should have a digit in the tens column. 5,150 joules to bring water from negative 15 or negative 25 degrees, excuse me, up to 15 degrees Celsius. Another example problem. How much energy is required to vaporize 225 grams of water at 20 degrees Celsius to steam at 150 degrees Celsius? Again, having my heat curve is going to help me set up this problem, and remembering where water turns to steam, what temperature that boiling point is. So we'll start here. Our first energy goes from 20 degrees Celsius up to the boiling point, 100 degrees Celsius. Then we'll need to vaporize that water. That'll be my second amount of energy. And finally, a third amount of energy to bring the steam up to 150 degrees. Again, my total amount of energy be Q1 plus Q2 plus Q3. Q1, my 225 grams of water, what's it going to take to get it from 20 degrees up to 100 degrees? That's 100 minus 20. Q1, 75,312 joules. It's quite a bit. Q2, now I need to vaporize that. Again, keep in mind we can't use that 334. That was to melt the ice. Now that we're vaporizing it, that number is different. It's 2,260 joules. So it's going to take, quite a bit of energy, 508,500 joules to vaporize that water. And finally, my third quantum of energy, bring that vapor up 50 more degrees. Again, notice I'm starting at 100, going up to 150. We already got to 100 over here. So it started at 100, we go up to 150. It's going to take 22,725 joules to bring that now steam up an additional 50 degrees. Final step, add together all of our Q1, Q2, and Q3. Watch your digits. And the digits are a little bit different this time. This one goes to the hundreds column. This one only goes to the thousands column. And this one goes to the hundreds column. Well, we're limited to the thousands column. So our final answer should only go to the thousands column. That 5 is going to have the 6 round up. And we'll end up with 607,000 joules. Problem 3 with a twist. So a very similar problem. We're starting at 20 degrees Celsius. We're going to 150 degrees Celsius. They are asking for the mass. So kind of outside the box, make you think a little bit here. And I've got my heat curve. I know that there's going to be 3 total problems. Q1 will bring up the temperature of the water to 100 degrees Celsius. Q2 will vaporize the water, and Q3 will bring up the value of the steam. So what I want to do, because I'm solving for mass, is solve as much as I can in terms of M. So Q1 is 334.72 times M. Q2, again, I have an unknown mass. My delta H vape is 2,260 joules per gram. So again, I've found, in terms of M, my Q2, 2260 M. And then finally, my Q3, again, I want to find in terms of M, 101 times M is equal to my Q3. Well, I can plug all of those in. I know my total Q. Now I've got a bunch of like terms. So I can add those like terms together, the 334.72, the 2260, and the 101. They're all times M. So I can add those together. Now I have what looks like a very reasonable algebra problem. 805,000 joules is equal to 2,695.72 times the mass, joule grams. So quite simply, divide both sides by 2,695.72 joule grams, and we're going to end up with 299 grams as our mass of water. Only 3 digits, because 805,000 only has 3 digits. Not too shabby, huh? Hey, as usual, this stuff takes practice. You just have to do it. Guys, I cannot highly recommend enough that you draw those heat curves. So up and over, up and over, up and over. Highly, highly recommend you draw those. You're going to need them to set up the problems, to know how many different steps you're making, to remind yourself of where to stop and make those adjustments. So again, give it a shot. Take a look. Do tomorrow.